Hi guys, welcome back to Zero Academy. In today's grade 12 physics lesson, we are going to be looking at electric circuits. We are going to start by revising series and parallel resistor networks, and then we are going to build on that knowledge by introducing an important concept, which is the electromotive force of a battery. We'll work through several circuit examples, so by the end of this lesson, you should be comfortable dealing with circuits containing both external resistors and the internal resistance of a real battery. Let's get started. The study of electric circuits is important because it helps us understand the technology involving electricity around us in the real world. In this chapter, we'll focus on revising some of the work you already learned in previous grades and adding on to your knowledge of the internal structure of a battery or a cell and how it influences what you already know about circuits. Now, series and parallel resistor networks. In grade 11, you learned about electric circuits, and these three quantities which are fundamental to dealing with electric circuits were introduced to you. First one is the electric current, which is represented by capital letter I, and that is defined as the rate of flow of charge through a circuit, and its formula is I is equal to V over R as derived from Ohm's law. The second one is potential difference of voltage, represented by capital letter V, and that is defined as the energy gained or lost per unit charge moving between 2 points of a circuit, and its formula is V is equal to I multiplied by R as per Ohm's law. And lastly, we have the resistance, which is represented by capital letter R and defined as internal property of a circuit element that opposes the flow of charge, and its formula is R is equal to V divided by I as per Ohm's law again. Now, we know that Ohm's law states that the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. V is equal to I over R. That is what that law is stating in mathematical expression. Circuits mainly consist of current, voltage, and resistance working together. There are two basic ways in which resistors can be connected in a circuit: series and parallel connections. Resistors in series and resistors in parallel have different features when talking about current, voltage, and total resistance. Let's start by looking at resistors connected in series. Resistors in series are connected end to end with no branches in between them, so the same current flows through each one of them. For n resistors connected in series, we have the following series connection. As you can see on my diagram, there are no branches between these resistors except for the one that is measuring voltage. That is not necessarily a branch, that is just a voltmeter, if you will. And we know that for n resistors connected in series, R total is given by R1 plus R2 plus R3 up to Rn. We add the resistors together, and the total voltage is V1 plus V2 plus V3 up until Vn, and again we add the voltmeters together. And lastly, we know that the total current is equal to I1 is equal to I2 is equal to I3. That means the current passing through resistors in series is the same throughout. We don't add up anything, it's just the same. It's the total current in the cell. Now let's move on to resistors connected in parallel. Resistors in parallel are connected across the same 2 points so that the voltage across each is the same and the total resistance is less than any single resistor. And here is a diagram illustrating resistors connected in parallel. If you can look closely, you will see that we have two main branches, branch 1 in yellow and branch 2 in red. The resistors in branch 1 are in series, and again the resistors in branch 2 are in series. But branch 1 is in parallel with branch 2 because there are gaps, or there are branches in between those resistors. And we know that for resistors connected in parallel, 1 over R total is equal to 1 over RB1 plus 1 over RB2 plus 1 over RB3 up until 1 over RBn. And we know that V total is equal to V of voltage of branch 1, voltage of branch 2, voltage of branch 3 up until voltage of branch n. That is, the voltage is the same across all resistors in parallel. And lastly, the current is equal to I1 plus I2 plus I3 up until In. That is, the current is not the same, it's divided in between resistors in parallel. Now let's move on to an exercise. You can see my diagram below. For the circuit below, Determine the current through the cell, the potential difference across R4, and lastly the current through R2. Let's start by the current through the cell. We know that 1 over Rp is equals to 1 over R2 plus 1 over R3 because R2 and R3 are in parallel. We're going to first calculate their total resistance. And substituting in my values, I will have 1 over Rp is equals to 1 over 10 plus 1 over 10. The bases are the same. We're going to go on and add the numerators, and that will give us 1 over Rp is equals to 2 over 10. And flipping both sides of the equations, we'll have Rp over 1 is equals to 10 over 2. That is, we exchange the numerators and the denominators. We flip them or switch them around, and that is going to give us an Rp value of 5 ohms. And now that we have resolved that parallel connection, all the resistors are in series now. Resistor R1, resistor R4, and the parallel connection are now in series, and hence the total resistance will be given by R1 plus Rp plus R4. Rp stands for parallel connection that we have just resolved, and substituting in those values we'll have Rs is equal to 20 plus 5 plus 15, and hence Rs is 40 ohms. And now going on to calculate the current, we'll have I is equals to V over R as per Ohm's law, and substituting in my values, I'll have I is equals to 75 over 40, and hence current is equals to 1,88 amperes. And we have solved that particular question. Moving on to question number 2, the potential difference across R4. First, we're going to say V is equals to IR, Ohm's law. Substituting in my values, I will have V is equals to 1,88 multiplied by 15, which is the resistance, and that will give us a voltage of 28,2 volts. And moving on to the current through R2. Again, we're going to introduce Ohm's law. V in parallel is equals to I multiplied by R. Substituting in my values, Vp is equals to 1,88 multiplied by 5, and that will give me a voltage value of 9,4 volts. Now we have the voltage. We're going to go on and calculate the current. I is equals to V over R again as per Ohm's law, and substituting in my values now I'll have I is equals to 9,4 divided by 10. That will give me a current value of 0.94 amperes. Now let's move on to the battery and internal resistance. Up until this point, we have been dealing with ideal or perfect batteries. That is, they are not affected by circuits or by current in any way. They provide a precise voltage up until the point where they run out. But when you measure the voltage across the terminals of a battery on its own, you will get a different value than when you measure it in a complete circuit. The value will be less when the battery is included in a complete circuit because of the current that will be flowing through it. This difference is sometimes referred to as lost volts. Real batteries are made from materials that have internal resistance. Hence, they are not just sources of voltage, but also possess resistance. Assuming that the total voltage of a source is referred to as an EMF or the electromotive force, then a real battery can be represented as an electromotive force connected in series with internal resistance R, small letter r, because that is the internal resistance. Now, let's take a look at the diagram here and define a new term called load. Load is the external resistance in a circuit, represented by capital letter R. If a battery has an EMF of E and internal resistance of R and is supplying a current I through an external load resistor R, then the voltage across the load resistor is that supplied by the battery. V load is equal to I multiplied by external resistance R. Similarly, from Ohm's law, the voltage across the internal resistance is V of internal resistance equals to I multiplied by internal resistance R, small letter r. The voltage V of the battery is related to its EMF E and internal resistance R by E is equals to external voltage multiplied by or plus internal voltage, that is E is equals to V plus I R. Let's take a look at the following exercise to emphasize what I was trying to explain to you earlier. Calculate the internal resistance of a battery that has an EMF of 21 volts and has a potential difference across its terminals of 18 volts when a current of 8 amperes is flowing through the battery when connected in a completed circuit. First, we're gonna introduce our formula. E is equals to V plus I over R. EMF is equals to external voltage plus internal voltage. And substituting in my values, I will have 21 is equals to 18 plus 8R. And solving for R, I will have 3 is equals to 8R, and dividing both sides by 8, I will have an internal resistance value of 0.375. Now let's move on to evaluating internal resistance in a circuit. Solving problems that involve internal resistance is simple enough. You just need to understand that what has been introduced to you before this chapter as a battery was simply just a source of EMF and a small resistor connected in series, and then solve the problem as you used to. Let's take a look at the following exercise to try and explain that concept a little bit better. For the circuit shown, determine first the potential differences V1, V2, and V3 across resistors R1, R2, and R3. Second, the resistance of R3. And lastly, if the internal resistance is 1 ohm, what is the electromotive force of the battery? Let's solve it. Potential differences V1, V2, and V3. First, let's start by V1. Obviously, V1 is equals to I over R1 from Ohm's law. And substituting in my values, V1 is equals to 12 multiplied by 3. 12 is the current as given by the question, and the 10 is the resistance as again given by the question, and that will give us a voltage of 120 volts. Next, let's move on to V2. Again, V2 is equals to I multiplied by R2 as per Ohm's law. And substituting in my values, I'll have V2 is equals to 12 multiplied by 30. The 12 is the current as given by the question, and the 30 is the resistance again as given by the question, and that will give us a V2 value of 360 volts. And lastly, let's go on and calculate V3. Now for V3, we're not going to do it as we did V1 and V2, because for resistance R3, we are not given the value. And hence, we're going to go in and say V total is equal to V1 plus V2 plus V3. And we're given the total voltage as 500 volts by the question if you look at our diagram at the bottom. And now substituting in those values, we have 500 is equals to 120 plus 360 plus V3. And solving for V3, we'll have V3 is equals to 500 minus 360 minus 120. And that will give us a V3 value of 20 volts. And now let's move on to calculate the resistance of R3. Now we know that V3 is equals to I multiplied by R3 from Ohm's law, and we know the voltage and the current, and hence we can go on and calculate the resistance. Now first let's substitute in the values that I already know. 20 is equals to 12 multiplied by R3, and dividing both sides by 12, I will have R3 is equals to 20 over 12, and hence R3 is equals to 1.67 ohms. And now let's go on and solve for the EMF of the battery, the last question. Electromotive force again is equals to the external voltage plus internal voltage. And substituting in my values, I will have E is equals to 500 plus 12 multiplied by 1, which is the internal resistance as per given by the question or the problem statement. And punching that into our calculators, we have an electromotive force of 512 volts. And that brings us to the end of that particular question. Now let's take a look at a different exercise. A battery of EMF E and internal resistance R is equals to 2 ohms is connected with resistors as shown in the diagram. First, what is meant by the term EMF of the battery? Second, the power dissipated in 40 ohm resistor is 2.25 watts. 2.1, calculate the current in the 40 ohms resistor. 2.2, calculate the reading on voltmeter V2. 2.3, calculate the reading on voltmeter V1. And lastly, calculate the EMF of the battery. Let's get straight to it. For the EMF, I defined it for you as the potential difference across the battery's terminals when it's not connected to a circuit. Second, let's go on and calculate for the current in 40 ohms resistor. We know the formula P is equals to I squared multiplied by R. It was introduced in grade 11. And substituting in everything I know into that formula, I will have 2.25 as my power, I squared, that is my current, I don't know it, multiplied by resistance, which is 40. I was given by the problem statement. And solving for I will have I is equals to square root of 2.25 divided by 40, and hence the current there is 0.24 amperes. Now let's go on and calculate the reading on voltmeter V2. I know that my current is 0.24 amperes. I've calculated for it before, and I'm just gonna write it at the top of my screen and introduce RP, or calculate for the total parallel resistance. 1 over RP is equal to 1 over 20 plus 1 over 20 again. If you can look at the two 20 ohms resistors, they are in parallel and are in series with the 40 ohms resistor. Now we're going to first solve for that parallel connection or parallel resistance. And we do that by saying 1 over RP is equal to 1 over 20 plus 1 over 20. And solving that a little bit further, we'll have 1 over RP is equal to 20, or 1 plus 1 all divided by 20, because the denominator is the same, and hence we add the numerators, and hence we'll have 1 over RP is equal to 2 over 20, and from there that is equal to 1 over 10, and cross multiplication RP is equal to 10 ohms, and hence the total equivalent resistance of the parallel connection is 10 ohms. And introducing Ohm's law, V2 is equal to I multiplied by RP. And now we can substitute in the values because we already know I and we know the RP, and we're gonna go and look for R. Now we can substitute in the values because we know the current and we know the equivalent parallel resistance. And substituting in those values, we'll have V2 is equal to 0.24 multiplied by 10, and hence V2 is equal to 2.4 volts. Now let's move on to calculating the reading on voltmeter V1. But before we even start, let's assess our circuit. If we look at V1, it's measuring the total voltage across the cell, across all the resistors, and hence it will require total resistance in that circuit. And to calculate for the total resistance, we're going to go on and say R external is equal to 40 plus 10. The 40 is the 40 ohms resistor, and the 10 is the equivalent resistance of the parallel connection, and hence the total external resistance is 50 ohms. And now we can go on and introduce Ohm's law. V2 is equal to I multiplied by R external, and substituting in our values, we know that V2 is equal to 0.24, which is the total current, multiplied by R external, which is 50, and that will give us a voltmeter reading on V2 as 12 volts. And now let's move on to the last part of the question, calculating the EMF of the battery. Again, we know that EMF is equal to V plus I multiplied by R, and substituting in our values, we'll have EMF is equal to 12 plus 0.24 multiplied by 2, which is the internal resistance as per given by the problem statement, and hence we'll have an EMF of 12.48 volts. And that brings us to the end of this lesson. Thank you for joining me, and I'll see you in the next one. Cheers.